All right. So today we are gonna make a parser for a subset of flow using the parser generator Gringo. So let me share my screen and let's just get started. Where is it here? All right, can you see my screen now?
Yes, we do. Yes, we can.
Perfect.
Yes.
All right. So we're gonna make it in here. I'm gonna call it pseudo flow because it's not the real thing. But let's just get started. And what I want to do is that I want to take just a small subset of flow, basically the lambda calculus, untyped, and just pass that into an AST using Gringo so you can see how that works. So the first thing I'm going to do is that I'm going to define the AST. So in a language, we'll have, I don't know, we'll have ints and we'll have bools and maybe strings and arrays, something like that. So what's a bool? That's a bool, an integer, a string, and an array. So this is an array value, so it has values inside. Let's say it like that. Okay, and then expressions, what are they? They are values, or it can be let binding, it can be a var, it can be a call, it can be a lambda, I think, and maybe an if statement, something like that. Then we have at least a minimal programming language. A let binding has an ID, it has a value, and it has a scope, like that. And a var is just an ID, and an if is a condition. It's a then branch, an else branch. And then a call is a function, and then it's arguments. In this case, I'm gonna do an array of arguments. You could also do one with curring and stuff like that, but this is fine. This is simpler. So a lambda, it takes a bunch of names, arguments, and has a body. Okay, I think that should be it. Yeah. So now we have the AST for a minimal language, and then we're gonna make the grammar for this thing. So an expression is equal. So let's just start with something very simple. Let's do an int. And this is the grammar for an integer. It's a sequence of these guys. All right. Gringo is an expression-based language. So what I'm doing here is that I'm defining a production called p expression, and I'm saying it's an int. Int in itself is a range of chars from 0 to 9, and one or more of those. And the entire program is then this expression. So somebody's chatting something. No sound. Okay.
Sound is okay.
Sound is okay, but some have problems with the sound. Okay, but that must be a local problem. All right, so this is like a minimal grammar for integers only. So let's just hook it up and say we're going to do a program. Whoops, not text, test. I meant to say test here. So what we're going to do is that we're going to, I think it's called Gringo Interpreter or something like that. Let's just see. I forget the name. Yeah, here it is. So this guy can take a grammar and parse it. So first you got to prepare the grammar. That's what you do with this guy, and then you can parse it afterwards. So let's do that. Our grammar is prepared like this. You got to give it the content of the file. I'm just going to use string include. That's a simple thing to do. So it's going to instantiate that string at compile time. Tools, Gringo, pflow, pexpression.gringo, I think. And it took an error reporter. I'm just going to do print ln for this. Okay, so now we have a grammar, and what we're going to do is we're just going to print that grammar after it has been prepared. Let's try that. Okay, run it, and there you go. It has now this grammar. So what you can see is that Gringo optimized the grammar. So it did pass it, but it can see it this can be inline, so to say. So it'll do that. Okay. So far so good. So let's try to also parse a string with this grammar, and you do that with this guy, and it takes a bunch of parameters. But let's take them one by one. Text is the string we want to pass. So we're going to say we have some code here. In this case, it's going to be an integer. What else did it want? Then it wants what's called Gringo typed operators. Now these guys are the semantic actions that you want to give to this guy, and you can easily construct it using it's this structure. So you give it a tree of operators for your language. So let me just write it up. So we'll have our expression operators, which is one of these guys. And it takes a bunch of trees of your nullary, unary, binary, and ternary and quadrary operators. So it's a helper that will make it easier to parse your language. That's what we want to give to this guy. In addition to that, you also want to give it an action handler. So Gringo has a stack discipline when it's parsing. The semantic actions will result in either verbatim values to be pushed on the stack or the thing it matches to be pushed on the stack. And to implement that, you got to give it a Gringo action. That's this guy. And as you can see, it takes two functions, polymorphic functions, either for adding an element of a given type on the stack or the match string on the type with the matched. And once again, there is a helper that can make this guy work for you. You take this guy, Gringo typed action, and construct that action thing. So let's say our action things is this. And what you have to do for this to work is to tell it how to construct a string from a string into your AST. So here, we got to do p string. That's how we make a string. Okay, and we also have to do the opposite. So given an expression, how can you construct this, get the string out of it? So this is something it needs inside to be able to do the semantic parsing. How to construct a bool, p bool, how to construct an int, p int, and a double. We didn't have doubles, so we'll just do a string for those at first. So we'll just say d to s. We can add doubles later. And then you also have to make lists. So in this case, you got to construct an empty list. So we can do an array, and then you got to be able to push on a list. So it's like cons. So you have a list and an element, and you got to push it on the list. And then you got to give it the operators. We already had those. That's these guys. Okay, so what you get out of this is now you have this action thing, which can interpret and run and construct your AST in a typed way. So in this particular typed action thing we constructed here is of this type, Gringo list of question mark. And question mark in our case is p expression. Okay, I don't know if this makes sense, but let's just import our AST like this, and then we gotta get, okay, we gotta make the empty array. It has to be an empty array, and we gotta get it the rest of the arguments, this one. All right, so let's continue. So we gave it the text, the operations, the action. Now we gotta give it the grammar, okay, which is our grammar from above. Then we gotta give it a default value in case the parsing fails. So we're just gonna say bool false, why not something, and an error reporter. All right. So there you go. So now this will give us our expression of p expression. You can see it gives our polymorphic value. So this is a typed parse that will give us this thing. All right, so I did something wrong somewhere. Argument number 4, 1, 2, 3, 4. let's just look at this guy. To int, okay, it gets strings. These guys are strings, and we got to convert them ourselves. That's the problem. So we'll just say s to I, and here we already have it as a string. What else does it say? Union of these guys, an array, something is wrong. Let's see, what did I do wrong? Argument number 7, 1, 2, 3, 4, 5, 6, 7. Here, so this one is, oh, it's an array itself. It's not, so this is P expression, right? So we got to expand it out. So we got to say switch on the L, and that's a P array with elements inside, and then we construct a new one of these guys. There you go. Okay. So when we do this, we say it didn't produce anything because we didn't put any semantics actions in our grammar. So what we can do is that we can say, okay, we want to return and the string we matched as a string. That's how you do it with the question mark here, no, the dollar sign here. And then it'll put a string in here. You can see now we have a string. That's the result of the parse. Okay. Let me just add an exit so we don't have to close all these windows like that. Okay, so what we need to do is that we're going to say, okay, we don't want an int as such. We want to convert it to an integer. That's a semantic action that it has some built-in actions that you can use. That's why we had to implement this this guy. That's going to be called now. So hopefully it'll return a p-int of this. Indeed it does. Okay. Questions so far? I know it's a little bit tricky, but I hope it's pretty clear. All right. If no questions, then we should do, let's do some more stuff. Let's do bools. Those are easy. So we can just say true, that's the string. And that's going to construct true. And false, false. So now we also have these guys. Okay. If we run it again, we can see that it still works, and we can try to give it true here. And now we get bool, true, and if we try it false, we also get that guy out. So far, so good. And what else do we need? I guess we need strings. A string starts with this guy, and then it's like any char except, so it's like a string, let's call it like this. So this is like any char. It's not a quote. Otherwise, any char will work. And you can do a range using hex like this. So like this, and we need to have 0 or more of these guys, right? That's a string. And to match that, we can match the entire thing like this. Let's see if that's correct. And let's try to put a string here. And indeed, we get it. But now we get it with the quotes and everything. So what we want to do is that we want to support escapes and stuff like that, like this. So what we can do is that we can add an operator. So now let's do the first operator. So we'll just do an operator that does an escape of a string. So this one takes a semantic actions where we get, it's a unary, these are unary operators. So we'll get this one, and now we have to, okay, let's do some helpers, values, export, get p string. We want to be able to extract the string from an expression. Like this, and for now we'll just do like this. And we have to import our AST. What did I do wrong? I gotta do pflow. So back in our semantic actions, now we get the string out. Now we have a string, and then we gotta deserialize it, unescape it. And we have that already. We have it as part of deserialization. What's it called? Deserialized string. This guy. I guess it's this one. Yeah. Deserialized string. That'll do escaping for us. So we'll just use this guy, and it returns the string and then the rest. So we'll just do first on this. That should be fine. Like this, and we gotta import it. Where was it? It was in text. Text deserialized string. Okay. And I call it with the wrong thing. We should call it with the string get p string out like that. And I have to import the values. So what am I doing wrong? Types. Okay, so now we get a string and we have to construct. This is the benefit of Gringo. It's strongly typed. So I can see now the result is not a p expression. It has to be a pre expression. I got a string and that's what it's telling me. So this is one of the advantages of this guy. What does it say now? Value is wrong. So expression has to be in value. And I think it's because this guy, it only takes values. So we'll rename this guy to be array value, and then we'll have array with expressions inside. So this is like an array constructor, while the other one is a value of arrays. Like this. Let's see if that helped. It did. It did. It did. And now we can see these actions are not exercised on escape. So this is also a nice feature of Gringo. It will tell you that you have this action, but it wasn't exercised by a grammar. So we recorded this action, but it tells me in the string you passed it wasn't used. And that's because we didn't call it. So let's call it on escape here. Okay. So now we should hopefully see that, yes, it did do it. All right, so continue in the grammar. So these, what values, do we have all the values now? And we need arrays as well. So let's do an array, and now we have to do white space as well. So we'll do that in a minute. Let's just rename it to that's expressions, and then an end, and that's gonna be an array. No, yeah, like this. Expressions, what's that? So that's an expression followed by a comma, a white space, and an expression, one or more of these guys, or the empty list, okay? Now, to capture the semantic values of these guys, there are built-in helpers called list and cons. So list will push the empty list on the stack, and cons will concatenate the element to the previous list, okay? So in this way, I can do it like this. That should be correct. And we need to define white space. White space is one or more space characters. And what are those? They are space or tab or new line. Let's do that at first. We can add comments later. But with this in place, let's just make sure we add it after each of the lexing terminals. All right, let's try that and see if that works. It ended here. It doesn't know the name expression. What's going on? What did I do wrong? Test passing ended here. Yeah, so it has this guy first. There you go. Okay, and let's try to pass an array. Of these guys with spaces and everything. That should be fine. And it didn't work. So what's wrong? Did I do a mistake? A list expression I don't know what I did wrong, but what I can do is that I can print the grammar and then I have a look at how it interpreted the grammar. So it says it's this thing. So it has this, yeah, that's because it's optional. That looks correct. But here it wants an int immediately after the array. So I guess I made a mistake. Yeah, I have to have the bar here. There you go. That was it. So let's see if that works. Now we print it and we get the empty array. So something went wrong. We didn't get the expressions into the array. So let's see what's going on here. Um, it didn't capture the values. Now, one of the things you can do is that you can debug your grammar by doing dump. When you do dump, then it'll print the stack you reach at that point. So here, the stack is 2 empty arrays after this thing. So something's probably wrong with our array constructs. Let's see. After here, now we have an int and an array. Okay, so maybe I swap these guys. Maybe it's the other way around with this guy. Let's try that. That's the one that does the const. And we have to, yeah, now it worked. You can see the end result here. So dump is useful. Yeah, there is another one that's print, that's just printing the top element on the semantic stack. Okie dokie. So now we have a grammar that can pass string arrays. All our values are done. Okay, good. Then let's proceed to do the rest of the grammar. So we need a let binding. You need an ID, and then you equals, and then an expression, then a semicolon, and an expression. And that's going to be let. Okay, so we have to define an ID. ID is a first, and then it's like a rest ID. First ID, rest ID. Let's do it like that. And then you want to match the entire thing as a string, and you want to allow white space after it. So first ID, the start of an ID is a char like this, or a capital one like that. And the rest is like the first ID, or we can do also digits. And oh, I forgot underscore, right? You can also use underscore and IDs like that. That should be an ID, and you've got to have a star on these guys. So that should pass the let thing. And now it says, again, I put the semantic action let in there, but it says it's unknown. So I get some help. I need to add that thing. And if we look at it, it has 1, 2, 3 things. So it's a ternary here, ternary. So it's one of these guys, and it's going to be let. And this one takes the ID, the val, and the body. And then we construct plet, get p string out of the ID, and then val and body, like that. So if we do that, now it says it's not exercised. So in my test program, I didn't exercise this production. So I'll just add it here and see if that works. Falling back to default value, passing ended here. So it couldn't pass it. Something is wrong in our grammar. So what did I do wrong? ID equals expression, semicolon expression. It looks correct. All right. So now it's because so let's print the grammar and see if we can figure out what's wrong. So this seems we didn't have ID, right? Just var, because I put a here and that's not passed yet. So we got to add var as well, just an ID. And let's do var for that guy. And that one is a unary operator. So let's put it down here and let's change this to pairs to tree like this. Now we'll have more of these guys. Let, and it gets, no, it's var. It gets an ID. And it's going to be p var get p string ID like that. Okay. And if we do that, now indeed we do pass the let as well. So we don't have to print the grammar. So that's let and that's var. What else is there? We have if, call, these three guys. So let's add them to the grammar. And if, all right, if, and then you want a space or non-letter, not letter, not one of these guys. That's not allowed here. That like this, and then, but you do want white space and then white space, and then it's an expression, VS, and then it's an expression, and it's else, and an expression. All right, and that's called if. I think like that. That should be correct. And it's a ternary operator if. So let's add it here. And it takes these guys and it constructs if like this. Okie dokie, and it says if is not exercised, so let's do that. If 1A else B. Let's try that. See if that works. So far, so good. And what was the next thing? It was call. So a call is it's a postfix operator because you can have a chain of calls. So now we're gonna see the next feature of Gringo here. So you have one of these guys, and then you have arguments, which are expressions, and then one of these guys. That's a call. But you can have multiple of them after each other. So what you're going to do is you're going to do it like this. Like that. Let's try that. And it's going to say I didn't define call. And call is a binary operator in terms of these guys. Parse to tree. And we got to be able to extract the values. We put it in here. Like that. Okay, and let's add a call up here. We'll just do it like that. That should be a call. And indeed it does. Let's see if we can call the result of that again. And you have a call and then a call, two calls. It seems to work. All right, so calls also done. And then we need lambda. Okay, lambda starts with one of these guys and then you get arguments, white space, and then this guy, and then an expression. Okay. Arguments, it's similar to this, except it's not expressions, but just IDs. Okay. And lambda is a binary operator, binary semantic action. So let's add it. These are the binaries. So it takes the args and the body. And then we get a say P array of args. It wanted strings. So we map these guys to get P string out of those guys and the body. That should do it. And let's add a lambda to our program. Lambda B So and C gives A, why not? Something like that. And it has a parse problem. So let's just simplify it and just do a lambda on its own to see if that works.
Is the grammar parser greedy itself? So you just arguments are more simple than previous line, and it couldn't be like expressions. Expression could be idea thing. So you should swap those lines between exps and args definitions.
Doesn't matter.
Doesn't matter. Okay.
So let's see what's going wrong here. The arguments, let's try. Once again, we'll just do the dump trick to see how far it gets in the pass, to see why it doesn't pass it. It pass it ended here. It doesn't even get started. So let's see what's wrong here. See if we get here. It doesn't even get there. So what am I wrong? What am I doing wrong? So once again, we'll just print the grammar to see what it did, to see if we can figure out what's going on here. So here, it has changed it to become an if first, and then otherwise this guy. That looks correct. I don't know what I did wrong. Oh, but the call thing is gone, right? So it has it here. I suspect it's because we gotta use the precedence operator. We gotta have different levels of the grammar. So I'll explain this in a minute, but let's just see if this is it. So what I did is that I added a precedence level. This thing changes the precedence so that this one binds looser than these guys that should bind stronger. So if you look at what happened is that the call up here, these expressions, they now refer to a next level here. And these guys in here, they refer to the top level. So you have this level of precedence going on. What am I doing wrong? Is it like this? Is that one? I don't remember. Oh, now it just, I think it just crashed. What happened? No, it's in an infinite loop. Something's wrong. Close the program. Oh, I have to do like this. I don't know if this works. Let's try that. Let's see. No, it does have it like, it's like double quoted. Is it a single thing I should have? Is it one? I don't remember the coding rules for backslash. Yeah, now this looks better. Okay, and now it worked. Now we have a lambda. So it was the coding rules about backslash. That's also tricky, always tricky. Okay, let's get back to the program. It says now it passed the lambda, but it didn't use all of the constructs. So let's just make sure we have a comprehensive test case. Like this, something like that. Why not? And it's not, let's drop the printing of the grammar. We don't need that anymore. And the only thing is a call. Let's just call the string. I know that's not correct, but let's just do that. So now the entire grammar is exercised, I think. Okay. I think that was all the different basic constructs. Now, in a real language, you want to have operators like plus, minus, and so on. So let's just add those. So plus or minus these guys. with white space. And here we're going to say that's plus and that's minus. And we can have more of those guys. Okay. And I need to add the binary operators. And we'll just convert that into, okay, what I'm going to do is I'm going to make a binary function here that helps us. It takes a and an operator, a and b, and it takes an operator and returns a function that takes 2 arguments. That's how it does it. And then they're going to do a call of p var of the operator name a and b, I think. Something like that. And it should be an array like that. What am I doing wrong? Oh, it needs a pair. Pair up like that. Okie dokie. And then what else is wrong? Array construction, something's not right. Oh, it's not, the function is inside here. Whoops, it's like this, right? Okie dokie. So we do plus, we do minus, and whoops. And let's just add the other guys we know we'll need in a minute. Multiplication, division, modulo, these guys. And let's just add them in here while we're doing it. Okay. So now we get this guy. And the thing about minus is that it has the associativity, the opposite of what comes out of the box. So here, now we say minus 1 and then in parentheses the other minus, which is wrong. You want to have it like this. And that reminds me we should add parentheses to the grammar. Let's just do that. Like that, that should do it. And if we do it now, it should already do it in the right thing. Now it's minus and then the 3 there. But we want that out of the box from this. Okay. Now Gringo has a nice little feature to help you do that. You just put this guy in front. Then you change the associativity and hopefully it'll do the right thing. Minus, minus, and then it's the other way around. Yep, now it works. And we can validate that we can have the correct precedence of these guys when you pass this. So it's like, oh my God, a minus, I guess it's this minus, no, the last minus, this minus, and then a plus, that's this guy, a 1, and then a division of 3 and 5, and then it's the middle time, that's 2 times 3, and you can see it does it correctly. So this is a...
Okay, Asger, can I have a question?
Yes.
Why do we have in Lingo third and fourth line we use pipes again, but not just vertical lines at the start of the line? Is it correct?
Here?
Yeah.
This is because of precedence, right? That's to make sure that this binds stronger than plus. So this is a Gringo feature that allows you to define the precedence of operators. So the way it works is that if I print what it produced, you can see it expands it into what you would write in Lingo. So in Lingo, we have all these guys expressed in 1, 2, 3, 4, 5, all the different precedence levels. But in Gringo, we have this nice feature with that pipe thing that does that for you.
Oh, okay.
All right. So far we have a parser that can parse these basic operators. I guess we got to do the rest of a language. We got to have comparisons. And I think, I don't remember the exact, but I think you have equals and then not equals. And then the other comparisons at the next level. Maybe I'm wrong about this one, who knows? But it shouldn't matter too much. And notice here, because it's a peg grammar, I have to put the less than or equal before the less than. A peg grammar is eager, so if I put this one first, it would always match that first, and that would be wrong. And for that reason, it's better to do it in this order, so it doesn't have to backtrack to pass the longer version. Okay, like this, and then I have to add the operators. Okay, so let's try to do this and see if that works. We can get rid of this print. And we have equals at the top, and then on the right-hand side, we have the less than. That's correct. Okay, so what else is there in a language? You have and or. Let's add those guys. And I think are they below equals? I don't remember. Does anyone remember? You know, what we can just cheat and look in the lingo grammar. Yeah, they're above comparisons, it seems. So you have or and then and. Okay, or and then and. Let's do this one. On and we got to do the operators. Okay, so let's test that. And A is not equal to 2, or B is bigger than 45. That should work. And it does pass. I don't bother checking it. It's most likely right. Okay, and then we need a negation and not, right? So we'll add them down here. Minus expression, that's negation. There's something wrong with syntax highlighting because of this backslash. So let me just move that to a production so we don't have this wrong. That's just the mode here that's not able to do the right thing. So let's put it at the end, then it doesn't ruin as much. All right, here, that's negation and not is the same thing, not, like that. And I think you have to put them up here, if I'm not wrong. I don't remember. Maybe it doesn't matter. Let's put them up here. I don't think that's gonna hurt anyone. Neg and not. These are unary operators. So let's add them here, and then let's make a unary operator. Minus and not. Okay, we gotta call it negate because minus is already used. Not a negate. We already did. Negate, not. Okay, and then we gotta define the UN thing here. So it's similar to this, except that it only takes one argument, like that. Okay, so let's see if we have and not. Indeed. Okay, so I guess we have sufficient things to make a small program and see if we can pass it. A good old classic is Factorial. So Factorial takes a number n, and oh, we don't have braces. That's interesting. We forgot about those. Sequence. If n is less than or equal to 1, then it's n. Else it's n times factorial n minus 1. Isn't that right? And then we'll call it on 5. That should be a correct program, except we didn't have brace. So let's just add braces. So we need the same thing like this, except that it's not commas, but semicolons that separate them. Okay. And this one should be a sequence. So we got to define sequence in here, p sequence. It's similar to array, except that the values, the result of this is just the last element. So, and then we have to define a unary operator for sequence. And that's going to be p sequence get p array of s's. Whoops. Like this. Correct? Okay, so let's try to pass that program. We just wrote here include tools Gringo pflow fact.flow. Okay. And indeed it has the program here. So now we have a simple parser for a small subset of flow. Did I forget any important syntax? Just for an example, anything you want me to add? I know it's not the complete grammar, but this should be a good start, right? No comments? I think that's it then. I think that should give you a good introduction to Gringo as a parser generator and how to set up the semantic actions, make sure the precedence and associativity is correct. The semantic actions are typed. There are nice helpers to make sure that the coverage is of your semantic actions so you can test your grammar. All of these nice tools is there. And with that, I'm going to say thank you. And that's it for today.
Can I ask a question?
Sure.
Just, I don't catch the difference between Gringo action and typed operators. Can you briefly explain the difference?
Yes. So in Gringo, when you have this operator, this question mark, no, a dollar sign, it means to push something on a stack. So the semantics of Gringo is that it's a stack machine. So this defines functions that basically will parse a string, and as part of that, as a side effect, put things on a stack. And that's what these guys do. So these guys, when I have these dollar signs, it'll just push those things on the stack. So here, when I have this guy, it pushes what I'm matching to the string. Now, as a special thing to push on the stack are actions. So there are some actions that will have other semantics. And that's what you define in these actions here. So this guy defines an interface for what some semantic actions do differently. So if we go and look at this guy and how it's implemented, so you can see here, Gringo actions get that action we give it. So this could be one of our actions. Let's say which one is a simple one. Let's say var here. So if we go here, it's going to look up in our tree of operators and find var here. So it's going to look up in that tree of operators I had before and find this function that does this thing. Okay, that's what it does in the unary operator. Now the way it works is that now it found that function in here. So it's going to pop from the semantic stack a value, and then it's going to call our function with that value. So now it calls this code with that thing it popped from the stack. And that's going to be pushed on the stack. Okay. So the way it works is that Gringo is pushing things on the stack, and then the semantic actions pop according to their arity of those functions. So that's why we have this setup with these typed functions, these operators, so that it can know how many arguments to pop, to push into our functions. I hope that helped. Any other questions? Well, if not, then okay. Thank you guys. Bye-bye.
Bye-bye.
Bye.